Hello, I'm Longxi from Zhejiang University. Now let me introduce you the work we have done in March last year, SF Team, a simple framework for enhancing quadrupedal robot at jumping agility by combining terrain imagination and measurement. In recent years, reinforcement learning using only proprioceptive sensors such as IMU and joint encoders has significantly enhanced the terrain adaptability of legged robots. However, this approach fails when encountering vertical walls or horizontal gaps in the environment. Robots must be accurately perceive their surroundings to make correct decisions. Common external sensors include LiDAR and depth cameras. Several studies have emerged that utilize these sensors to enhance the jumping capabilities of quadrupedal robots. Depth camera-based frameworks require accounting for latency and simulating depth, leading to substantial GPU memory consumption during training. Additionally, such frameworks often rely on distillation strategies, with performance limited by the teaching model. A LiDAR-based approach was proposed by ISL last year. Their navigation-based methods featured complex architectures composed of numerous modulars, complicating both training and engineering debugging. Our goal is to leverage LiDAR and employ a straightforward approach to enhance the jumping capability of quadrupedal robots. We follow the classical acticritic framework. The robot's observations include classical observations flagged sim to real RL and the elevation map. The critical input comprises the robot's observations, velocity, elevation, and parameters about domainization. To accelerate and improve the convergence of the policy, we incorporate prior gradients into the history encoder and terrain encoder. We adopt the context encoder from DreamWorks, utilizing a variational autoencoder to predict robot velocity and future observation. We applied a vanilla autoencoder to terrain, since we introduced noise to the input evaluation map to facilitate sim-to-real learning. This structure also helps the network learn to reduce noise through dimensionality reduction. We train proposed framework on 5 terrain types: rough terrain, irregular rocks, steps, horizontal tabs, and vertical walls. We also introduce a novel reward function that enables the robot to track virtual slopes during jumps, thereby enhancing training in top 5. Other classical training techniques, including curricular learning, domainization, and reward shaping, are also adopted. We conduct ablation studies and comparative experiments in simulations to validate the effectiveness of prior gradients and rewards. For real-world deployment, we maintain a globe map and capture the robocentric elevation map at a 200 Hz frequency, achieving zero-shot sim to real. We deploy our framework on X30 and Light 3, respectively, conducting repeated experiments in challenging scenarios such as raised platforms and ditch crossing. The X30 jumps up and down the platform 3 times consecutively, with the final landing into a cluster environment where the quadrupedal robot's curve becomes entangled with flexible debris. For Light 3 equipped with only one LiveVox LiDAR, we construct the scenarios with staircase, gap, low step, and high platform. As we can see, the Light 3 successfully traversed the terrain twice. More test videos and demos of our recent work can be viewed by scanning this QR code. You can also scan this QR code to learn more about me and my other projects. Thank you.